Welcome to the deep dive. You know, sometimes you just want to get your head around a complex topic,
Yeah.
right, without wading through tons of text. Well, that's what we do here. We distill the key stuff for you.
Yeah, try to make it digestible.
Exactly. And today, we're plunging into artificial intelligence. Our main guide is Arnav Bhatnagar's AIfundamentals.pdf.
Good starting point.
Yeah, and we look at various sources, but our mission today is really to synthesize this so you can grasp the AI basics.
And it's interesting, the document kicks off by thinking about us, about humans, our knack for building tools. It sees that creativity as pretty fundamental.
Right. Which sets things up perfectly for AI, doesn't it? Because, isn't AI fundamentally a new kind of tool? Maybe an incredibly powerful one.
Definitely. And the document mentions this idea of tools technology.
Nice.
Yeah, technologies that don't just tweak one little thing that could potentially, reshape a whole economy, maybe even society.
Like ChatGPT is already starting to do, maybe. Changing how we write, work.
It's a potential example, yeah. And zooming out, there's this related concept, general purpose technology.
Yeah.
These are the real heavy hitters, like language itself, huge impact everywhere. Or the plow, the printing press.
The car, the computer.
Yeah,
Things that change everything, not just one sector.
exactly. And the document notes how they often augment us physically, like the plow, or cognitively, like the computer.
So each of those really shifted history. The computer boosted our thinking power, which leads to the big question the document kind of poses. Is AI the next one? The next GPT, boosting our cognitive abilities even more?
It's a really compelling question, especially when you bring in Andrew Ng's view, which is in the document. He says it's hard to think of an industry AI won't change soon.
Wow. That suggests that same kind of pervasive, maybe revolutionary potential we saw before, like the internet, maybe even bigger.
Could be. The reach seems potentially enormous across almost everything we do.
So, okay, if it's this potentially huge thing, where did it all start? We should probably look back a bit, right? The document flags a key starting point.
It does. The Dartmouth Summer Research Project, July 1956, that's widely seen as the moment AI really became, a formal field of study.
1956, wow. And since then, there have been some pretty startling advancements. The document points out a couple of milestones that maybe surprised people.
Oh, absolutely. The pace in certain areas has been remarkable, like IBM's Deep Blue beating Garry Kasparov at chess. That was huge back then.
I remember that. A big moment.
Definitely showed AI could handle deep strategy. And then, maybe even more surprising, AI beating a top human player at Go.
Why more surprising?
Well, Go is often seen as more intuitive, less about brute calculation than chess. So that victory suggested AI was developing something, well, more nuanced, perhaps.
That really hammers home Andrew Ng's point again, doesn't it? If AI can conquer these complex games and potentially transform industries, the implications for you listening are pretty massive, whatever you do.
For sure. So we get that it could be huge, but how does it actually work? Like fundamentally, the document starts breaking this down.
Right. The basic flow. Input, processing, output. Simple enough. And the spam filter example is perfect. Emails come in, that's the input. The spam filter does its thing processing.
Yeah.
And the output. Email sorted into spam or not spam. We all see that.
Exactly. And driving that processing bit is the algorithm.
Okay, the algorithm.
But the document calls it a step-by-step guide for solving a problem. The Lego instructions analogy is great, actually.
Yeah. Follow the steps, build the thing.
Right. The algorithm tells the computer the steps to get to the solution.
Got it. Input, algorithm, processes it, output. And the document says the early AI, the first attempts, were mainly these things called rule-based algorithms.
That's right. Back in the, say, 1950s through the 80s, that was the main approach. You'd explicitly code rules, input goes in, the rule-based algorithm checks its rules, produces an output. Think lots of if-then statements.
Okay. If email contains Viagra, then mark as spam. Something like that.
It's sort of, yeah. But as the document points out, that had some big limitations.
Like what?
Well, these systems couldn't really go beyond the rules they were given. They couldn't learn or discover things if the rules weren't already known.
And the real world.
Yeah.
It's not always clear-cut rules, is it? It's messy.
Exactly. It's chaotic, unstructured, not always predictable. Which brings us to what the document calls Polanyi's paradox.
Polanyi paradox. Okay, what's that?
The core idea is we know more than we can tell.
We know more than we can tell.
Huh?
Like riding a bike, I know how, but explaining every muscle movement, impossible.
Precisely. So much of our knowledge is tacit, intuitive. It's
Yeah.
incredibly hard to write down as explicit rules for a computer. Try writing rules to recognize any cat in any photo. It's tough.
Right. Different angles, lighting, breeds. So that paradox shows why those early rule-based systems hit a wall with real-world stuff. They needed something more flexible.
Yeah, they needed a way to learn to adapt beyond just the pre-programmed stuff, and that limitation really pushed AI to evolve. The document gives a nice timeline.
Okay, yeah. So 50s to 80s,
Mm-hmm.
mostly rule-based. Then the 90s and 2000s saw rule-based still, but also machine learning and deep learning starting to emerge.
Correct, a mix. And then from the 2010s onward, ML and especially deep learning have really taken center stage.
So what's the big shift? Rule-based versus machine learning.
The fundamental difference is how the program or intelligence gets created. Rule-based is basically input plus code's output.
Okay.
Machine learning is more like input, which is data, plus computation, that's the training part, DAF program, which we call a model. And that model then gives you the output for new inputs.
Ah, okay. So instead of human writing all the rules in the code,
Right,
the machine learns the rules or patterns from the data you feed it.
exactly. The system learns from examples, and deep learning, that pushes it further. It uses huge amounts of data, plus code, plus a specific structure called a neural network.
Neural network, got it. Big data, and these networks are key for deep learning.
They are. The scale and the network structure are what unlock a lot of its power.
The document uses recognizing handwritten numbers as an example here, which makes sense. Trying to write rules for every possible 7 felons. All the loops, slants, scribbles.
Yeah, it would be a nightmare. Rule-based would really struggle, all those tiny variations. But with machine learning, you don't write the rules. You just show it thousands, millions of examples of handwritten numbers already labeled 1, 2000, N, etc.
And it figures out the patterns itself?
It learns to associate the visual patterns with the correct label. That's the core idea.
It's a totally different way of thinking about programming, isn't it? The document contrasts them. Traditional is input plus program output. ML is input data plus computation training program model output. That training step is the magic ingredient.
It really is. That's where the learning happens. And deep learning heavily relies on these things called neural networks. The document compares them to the brain.
Right, like our brain has neurons firing.
Interconnector.
Neural networks have these artificial neurons or nodes connected up.
That's the basic idea, yeah. Computer programs loosely inspired by brain structure, designed to help machines learn from data and make decisions.
And the structure. The document breaks it down using a basketball player height example. Tall or short?
Right. 3 main layers, usually. First, the input layer. That's where the raw data goes in, so for the player. Height, weight, shoe size, maybe.
Okay, the raw facts.
Then you have 1 or more hidden layers. This is where the network does its heavy lifting, processing the inputs, finding patterns through calculations across the nodes. More hidden layers often means it can learn more complex stuff.
The thinking part, sort of.
You could say that. And finally, the output layer. This gives the network's final answer. In the example, maybe just one node saying tall or short.
Input, hidden layers, output. Simple enough structure. But how does it learn?
Ah, the training process. The document outlines the steps nicely. Step 1, feed it data. Lots of labeled examples players you know are tall or short with their stats.
Okay, give examples.
Step 2, it makes a prediction. Just a guess, especially at first. Probably wrong.
Step 3, check for errors. Compare the guess to the right answer. How far off was it?
Crucial step, because step 4 is adjust. Based on the error, the network tweaks its internal connections, the weights between nodes, to try and do better next time. There's an algorithm called backpropagation that manages this adjustment.
Learning from mistakes.
Pretty much. And step 5, repeat. You do this over and over, feeding it data, predicting, checking, adjusting thousands or millions of times. It gradually gets better and better.
Continuous improvement through practice.
Exactly. And these aren't just theoretical things. The document lists examples you definitely use. Face recognition on your phone.
Yep.
Spam filters.
Daily.
Self-driving car features. Language translation like Google Translate.
All neural networks underneath.
Heavily reliant on them, yes. It's amazing how this brain-inspired idea powers so much tech now.
It really is. Okay, so we've got neural networks powering deep learning. But the document also stresses the difference between machine learning and deep learning. They aren't quite the same.
No, exactly. Deep learning is a type of machine learning, a subset. The document has a handy table comparing them.
Right. Let's break that down definition-wise. AI is the big umbrella. ML is a part of AI, learning from data. DL is a part of ML, using these multi-layered neural networks.
Perfect summary. And their approach differs too. Early AI was rule-based. ML learns from structured data, often needing humans to define the important features first. DL uses neural nets to often find the important features automatically from raw data, which is a big deal.
Well, automatic feature finding. Interesting. How about the spam example again?
Good one. Rule-based AI. If email has free money, it's spam. Simple rule.
Okay.
ML approach. Analyze word frequencies, maybe sender reputation from labeled spam examples to build a classifier.
More sophisticated.
Yeah. DL approach. Feed the whole email content into a deep neural network. Let it figure out the complex patterns, the subtle cues, the context that indicate spam. Potentially much more powerful for tricky cases.
Got it. And feature extraction ties into that.
Mm-hmm.
ML often needs manual help. DL does it more automatically.
Generally, yes. In traditional ML, you might spend a lot of time figuring out which data features are most predictive. With DL, especially for things like images, the network often learns the relevant features, edges, textures, shapes by itself through its layers.
That sounds efficient. What about data needs?
Big difference. Rules might work with little data. ML usually needs a decent amount of labeled data. Deep learning, though, it often thrives on massive data sets. Those complex networks have millions of parameters to tune. They need lots of examples to learn effectively.
More data, more power, basically.
Often, yes. And that usually means more computation, too. Training big, deep learning models takes serious computing horsepower. GPUs are essential.
Makes sense. Okay, before we get into specific ML and DL techniques, the document clarifies some key terms using a house analogy.
Yeah, it's quite helpful. An algorithm is like the blueprint, the instructions on how to build the house.
Okay, the step-by-step.
The model is the finished house, the trained AI system ready to do its job.
The result of the training.
Right. A technique is like a building method, modular construction maybe. A general approach.
Like supervised learning is a technique.
Exactly. And architecture is the overall design style of the house, modern, colonial. In AI, it's the specific structure of the model, especially for neural networks like a CNN or a transformer architecture.
Blueprint, house, building method, design style, algorithm, model, technique, architecture. Okay, that clicks. So let's talk techniques. Starting with machine learning, 3 main types.
Yes, the document breaks it down into 3 big categories: supervised learning, unsupervised learning, and reinforcement learning.
Okay, supervised first. The name suggests guidance.
Precisely. You train the model on data that's already labeled with the correct answer. Input comes with the known output. The model learns the mapping between them.
Like the handwritten digits you show it a 7 and tell it this is a 7.
Exactly, or the medical diagnosis example. Symptoms, input, linked to the known disease, output. It learns to predict the disease from new symptom sets.
So it's good for predictions, classifying things.
Right. Predictions, classification, also regression, which is predicting continuous numbers. The document lists key algorithms: linear regression for things like house prices, logistic regression for yes-no classifications like spam,
Okay.
decision trees for rule-like classifications, maybe medical diagnosis flows, support vector machines, SVMs, good for finding boundaries between classes, like in face recognition. And neural networks can also be used here for complex stuff like speech recognition.
Got it. Supervised, learning with labels. What about unsupervised?
The opposite, really. Here, you give the model data with no labels, no right answers provided. The goal is for the algorithm to find hidden structure or patterns in the data all by itself.
Find patterns on its own. Like what?
The customer segmentation example is classic. An online store has loads of customer data purchases, clicks, etc. Unsupervised learning can automatically group customers into segments, maybe bargain hunters, high spenders, new parents, without being told those categories exist beforehand.
Ah, it discovers the groups. So it's good for finding structure, grouping things.
Exactly. Grouping, finding structure, pattern recognition. Key techniques include clustering algorithms like k-means, grouping similar items, association rule learning, like a priori finding things that often occur together, like people who buy diapers also buy beer, the classic market basket analysis.
Right.
And also things like principal component analysis, PCA, for simplifying complex data while keeping the important bits, useful for things like image compression.
Okay, makes sense. Supervised needs labels. Unsupervised finds structure in unlabeled data. What's the third one? Reinforcement learning.
Right. This one's different again. It's about learning through interaction and feedback. An agent takes actions in an environment and gets rewards or penalties based on the outcome.
Learning by trial and error, kind of. Like training a dog with treats.
That's a decent analogy, yeah. The agent wants to maximize its total reward over time. The self-driving car example is good here. The AI agent driving the car gets positive rewards for staying on the road, obeying rules, reaching the goal. It gets penalties for hitting things, going off-road. Over many trials, it learns the optimal driving policy.
Learning what actions lead to good outcomes. Where is this used?
It's big in robotics, teaching robots complex tasks. Gaming AI, I think AlphaGo learning to beat Go champions. And any kind of real-time decision-making where you need to adapt based on feedback. Algorithms include Q-learning, deep Q networks, which add deep learning, and policy gradient methods.
Fascinating. Okay, that covers the main ML techniques. Now, let's dive deeper into deep learning techniques specifically. These are mostly about different neural network architectures, right?
Primarily, yes. Different architectures are suited for different kinds of data and tasks. The document highlights several key ones. First up, convolutional neural networks, or CNNs.
CNNs. I hear about those a lot with images.
Exactly. They're designed for grid-like data images, video frames. They use special layers, convolutional layers, with filters to automatically detect spatial patterns, edges, textures, shapes, and eventually complex objects.
So they see features in pictures.
In a way, yes, they learn a hierarchy of features. Little features combine to form bigger ones. They also often use pooling layers to make the process more efficient.
And used for.
Obvious ones. Face recognition, analyzing medical images like X-rays, and crucial for self-driving cars to detect pedestrians, signs, other cars. Anything visual, really.
Makes sense. Next up, recurrent neural networks. RNNs.
Right. These are built for sequential data where order matters. Think text, speech, time series like stock prices.
What makes them recurrent?
They have loops. The output from one step feeds back in as input to the next step. This gives them a kind of memory, allowing them to consider previous elements in the sequence when processing the current one. Context is key.
So they remember what came before.
They try to, yes. That's vital for understanding language, where word order changes meaning or speech. So, uses include speech recognition, Siri, Alexa, language translation, maybe stock market prediction.
Okay. But I've heard RNNs can have memory issues.
They can struggle with long-term dependencies, remembering things from way back in a long sequence, which leads us to long short-term memory networks, LSTMs.
LSTMs. An upgrade to RNNs.
Pretty much. They're a more complex type of RNN, specifically designed to overcome those long-term memory problems. They use special gates. Think of them as controllers that regulate what information gets stored, forgotten, or passed on in the network's memory.
Smarter memory management.
Exactly. They can selectively remember important stuff over longer stretches. So they're great for chatbots needing to recall earlier parts of a conversation, predicting customer behavior over time, even handwriting recognition.
Better memory, better performance on long sequences. Now, transformers, they seem to be everywhere now, especially with language.
Absolutely huge breakthrough. Models like ChatGPT, BERT, they're based on the transformer architecture. They kind of revolutionize natural language processing.
How are they different from RNN SLSTMs?
A key difference is they don't process sequences step by step. They use a mechanism called self-attention to look at all the words in a sentence or sequence at the same time.
All at once.
Yeah, essentially. It allows the model to weigh the importance of every word relative to every other word, no matter how far apart they are. This captures context much more effectively, especially complex relationships.
That sounds powerful and efficient.
It is. That's why they excel at tasks like advanced chatbots, much better search engines, Google uses them, and things like summarizing long texts really well.
Okay, transformers are big for language. What's the last one? Generative adversarial networks. GANs. Sounds dramatic.
They are pretty cool. Their main goal is different. It's to generate new data that looks like the training data, creating images, music, text.
Creating new stuff.
It's a two-player game, essentially. You have two neural networks, a generator and a discriminator. The generator tries to create fake data, say fake celebrity photos. The discriminator tries to tell the difference between the generator's fakes and real photos from the training set.
They compete.
Exactly, adversarially. The generator gets better at making fakes to fool the discriminator. The discriminator gets better at spotting fakes. This competition pushes the generator to create incredibly realistic outputs.
Wow, like an art forger and an expert detective training each other.
Great analogy.
Sure.
And the results, we see them in deepfake videos, stunning AI-generated art like DALL-E or Midjourney, even creating realistic environments for video games.
Okay, that's quite a tour of the techniques. So, wrapping this up, We covered a lot.
We really have, from AI as a potential general-purpose technology.
Yeah, building on that idea of tools augmenting us, this time cognitively.
Through its history, the basic concepts, the shift from rules to learning from data with ML.
And then the power of deep learning with neural networks.
We looked at the key differences, the terminology, the main ML techniques, supervised, unsupervised, reinforcement learning.
And then the big DL architectures.
Hmm.
CNNs for images, RNN, SLSTMs for sequences, transformers for language understanding, and GANs for generation.
It shows a clear evolution, right, towards systems that can learn more complex patterns from vast amounts of data, often needing less human handholding and defining features.
Definitely. So thinking about all this, especially these recent powerful techniques like transformers and GANs, it leaves you wondering, doesn't it?
What's next?
Yeah. As this stuff gets woven deeper into everything we do, our jobs, our lives, what are the possibilities, maybe the challenges that we haven't even thought of yet?
That's the big question, isn't it? With the pace of change we're seeing, predicting the truly unforeseen consequences, well, that's something to really mull over. It's a landscape that's shifting under our feet.